Welcome to Math for Sleep. It's lovely to have you here. Before we begin tonight's journey into one of mathematics' deepest mysteries, I'd love to know where in the world you're watching from. A quiet bedroom with the lights dimmed low, a late-night study session that's slowly winding down, perhaps curled up on a cozy couch with a blanket wrapped around your shoulders. Wherever you are, I hope you're comfortable, settled in, and ready to drift gently into a story that has captivated the greatest mathematical minds for more than 2,000 years. If you enjoy these relaxing mathematical explorations and would like to hear more about the beautiful puzzles that fill our universe with wonder, a like and subscribe really helps this sleepy little channel continue its journey through the landscape of numbers. And to those of you already subscribed, thank you. Truly, your support means more than you know. Now, I'll try not to make tonight's topic so intriguing that it keeps you wide awake, but if it does, at least you'll have stumbled into one of the oldest, most stubbornly persistent questions in all of mathematics. A question so simple that a child could understand it, yet so profound that 20 centuries of brilliant minds have failed to answer it. A problem that began in ancient Greece, traveled through medieval monasteries, puzzled Renaissance scholars, frustrated Enlightenment geniuses, and continues to challenge modern supercomputers working day and night in search of a single example or a definitive proof. So, let's begin, shall we? Let's drift together into the mystery of odd, perfect numbers. A search for something that might not exist, a quest that has consumed countless hours of human thought and computation, a mathematical ghost that haunts the landscape of number theory, always just out of reach, never quite appearing, never quite proven impossible. Imagine you're holding a number in your mind. Let's say the number 6. 6 apples, 6 days, 6 anything. Now imagine taking all the numbers that divide evenly into 6, all except 6 itself. Those would be 1, 2, and 3. 1 goes into 6, 2 goes into 6, 3 goes into 6. Now here's where something magical happens. Add them together. 1 plus 2 plus 3 equals 6, the number you started with. This is no accident. This is no coincidence. This is a property so rare, so special, that ancient mathematicians gave it a name that suggested divine perfection. They called numbers like 6 perfect numbers, not perfect in the sense of flawless or ideal, but perfect in a precise mathematical sense, a number whose proper divisors, when summed together, equal the number itself. Think about how unusual this is. Take almost any number and try it. 7. Its only divisor other than itself is 1, and 1 doesn't equal 7. 8. Its divisors are 1, 2, and 4. Add them up. 1 plus 2 plus 4 equals 7, not 8. 9. 1 and 3 are its proper divisors. 1 plus 3 equals 4, nowhere near 9. But 6 works. 6 is perfect. And after 6 comes 28. The divisors of 28 are 1, 2, 4, 7, and 14. Add them together. 1 plus 2 is 3, plus 4 is 7, plus 7 is 14, plus 14 is 28. Perfect. After 28, you have to wait a long time. The next perfect number is 496, then 8128. Then the numbers start getting large, astronomically large, numbers so vast they would take pages to write out. Here's what we know for certain. All of these perfect numbers, every single one we've ever found, has something in common. They're all even. 6 is even. 28 is even. 496 is even. The 52 perfect numbers we've discovered, the largest containing more than 41 million digits, are all even. And here's the question that has haunted mathematicians for 2 millennia. Does there exist an odd perfect number? Is there somewhere, hiding in the infinite landscape of numbers, an odd number whose proper divisors sum to itself? Or are all perfect numbers doomed to be even? A cosmic rule woven into the fabric of mathematics itself? This is not an idle curiosity. This is not a puzzle for puzzle's sake. This question reaches into the deepest foundations of how numbers work, how they relate to each other, how patterns emerge from the chaos of arithmetic. It connects to prime numbers, to divisors, to the fundamental building blocks of all mathematics. It has resisted solution not because mathematicians haven't tried, but because every attempt, every approach, every clever trick has led either to another restriction, another condition an odd, perfect number would have to satisfy, or to computational exhaustion, checking trillions upon trillions of numbers without finding a single example. The problem is simple enough to explain to anyone. You don't need advanced mathematics to understand the question. But to answer it, that has proven to be beyond the reach of human knowledge for over 2,000 years. And that's where we'll spend our time tonight, drifting through this beautiful, frustrating, endlessly fascinating mystery. Before we venture deeper into the forest of perfect numbers, let's take a moment to become comfortable with the language we'll be speaking. Don't worry if numbers have never been your favorite companions. We'll move slowly, gently, letting each idea settle before moving to the next. There's no rush tonight. We have all the time in the world to explore these concepts, to let them unfold naturally, to understand how they connect to each other and to the larger mystery we're pursuing. When we talk about divisors, we're talking about a kind of mathematical relationship that's as old as counting itself. A divisor of a number is simply another number that divides into it evenly, with no remainder left over. If you can split a number into equal groups using another number, that second number is a divisor. It's a relationship of perfect division, of clean separation, of numbers fitting into each other like puzzle pieces designed to match. Take 12, for instance. It's a friendly number, a number we encounter often in daily life. 12 eggs in a carton, 12 months in a year, 12 hours on a clock face. And 12 has many divisors, many numbers that fit into it evenly. You can divide 12 by 1 and get 12. You can divide 12 by 2 and get 6. You can divide 12 by 3 and get 4. You can divide 12 by 4 and get 3. You can divide 12 by 6 and get 2. And you can divide 12 by 12 and get 1. So the divisors of 12 are 1, 2, 3, 4, 6, and 12. Each of these divisors tells you something about 12's structure. The divisor 2 tells you that 12 can be split into 2 equal parts of 6. The divisor 3 tells you 12 can be split into 3 equal parts of 4. The divisors reveal the hidden architecture of the number, the ways it can be decomposed and reconstructed, the patterns embedded in its mathematical DNA. Now, mathematicians make a small but important distinction here. When we're looking for perfect numbers, we care about proper divisors. These are all the divisors except the number itself. So the proper divisors of 12 are 1, 2, 3, 4, and 6. Everything except 12. This makes intuitive sense when you think about it. We're asking, what are the building blocks of this number? What pieces can we extract from it? And the number itself isn't really a building block. It's the whole thing, the finished product, not a component part. If you add up the proper divisors of 12, you get 1 plus 2 plus 3 plus 4 plus 6, which equals 16. That's more than 12. So 12 is not perfect. In fact, 12 is what mathematicians call abundant. It has so many divisors that they add up to more than the number itself. It's like having more pieces than you need to build something. The parts exceed the whole, which has its own mathematical poetry, even if it's not perfection. Many numbers are abundant. Take 24. Its proper divisors are 1, 2, 3, 4, 6, 8, 12, and 12. Wait, did I say 12 twice? No, just 12 once. But the sum is 1 plus 2 plus 3 plus 4 plus 6 plus 8 plus 12 equals 36. That's much more than 24. 24 is quite abundant indeed. On the other hand, some numbers have too few divisors. Prime numbers, for instance. A prime number's only proper divisor is 1, because by definition, a prime number cannot be divided evenly by any number except 1 and itself. 5 is prime. Its only proper divisor is 1. 1 is less than 5, so 5 is deficient. It doesn't have enough divisors to be perfect. It's too sparse, too simple in its structure. Most numbers are deficient. This is actually quite surprising when you first learn it. You might expect numbers to be evenly distributed among deficient, perfect, and abundant categories. But they're not. The vast majority of numbers are deficient. Abundant numbers are less common. And perfect numbers, they're vanishingly rare. Perfect numbers sit right in the middle of this spectrum. Not abundant, not deficient, but just right. The Goldilocks of numbers. Their divisors add up to exactly themselves, no more, no less. It's a delicate balance, a mathematical equilibrium that seems almost intentionally rare, almost impossibly precise. It's like finding a seesaw that's perfectly balanced, not tilting left or right, but hovering in exact horizontal symmetry. The ancient Greeks, particularly the followers of Pythagoras, saw deep significance in this. They believed that 6 was perfect not just mathematically, but cosmically, not just numerically, but spiritually. God created the world in 6 days, they reasoned, because 6 was a perfect number. The moon orbited in 28 days because 28 was perfect. These weren't mere coincidences to them. They were signs of divine mathematical order underlying all of creation, evidence that the universe itself was constructed according to mathematical principles. That number was not just a human invention, but a fundamental reality. St. Augustine, writing in the early 5th century, echoed these sentiments. In his massive work, The City of God, he wrote that God could have created the world in an instant, but chose 6 days because 6 is the first perfect number. The choice was deliberate, meaningful, a reflection of divine attention to mathematical harmony. Philo of Alexandria, writing in the 1st century, also noted the connection between 6 and creation, seeing in it evidence of purposeful design. Later, medieval scholars would build elaborate numerological systems around perfect numbers, seeing in them connections to theology, cosmology, astrology, and mysticism. We might smile at such mysticism today, but there's something undeniably compelling about perfect numbers. They feel special. They feel rare and precious, like finding exactly the right word in a poem or hitting exactly the right note in a song. And their rarity is not an illusion. Perfect numbers are genuinely, provably, exceptionally scarce. This is not mere intuition or poetic fancy. It's mathematical fact. Think about it this way. Among all the counting numbers, among the infinite march of 1, 2, 3, 4, and onward forever, only 52 perfect numbers have ever been found. 52. In all of infinity, we know of 52, and every single one of them is even. Let that sink in for a moment. 52 perfect numbers out of infinite numbers. That's not just rare. That's almost impossibly rare. To put this in perspective, there are infinitely many primes, infinitely many squares, infinitely many numbers divisible by 3, but only 52 known perfect numbers. And we strongly suspect that if there are infinitely many perfect numbers, which is itself unproven, they become rarer and rarer as numbers grow larger, separated by vast stretches of non-perfect numbers, isolated islands in an infinite ocean. This rarity is part of what makes perfect numbers so fascinating. They're not just mathematically interesting. They're mathematically precious, like finding diamonds in a field of rocks. Each one is a treasure, a discovery worth celebrating. And the question of whether odd numbers can join this exclusive club, whether odd perfection is possible, becomes all the more tantalizing because of how rare even perfection is. Around 300 years before the Common Era, in the Great Library of Alexandria, a mathematician named Euclid was compiling what would become one of the most influential works in human history, the Elements. This wasn't just any mathematics textbook. It was a systematic, logical, beautifully organized presentation of all the geometry and number theory known to the ancient world. In Book 9 of the Elements, toward the end of his treatment of numbers, Euclid presented a remarkable formula. Not a formula in the modern algebraic sense, mind you. Euclid didn't have our notation, our symbols, our tidy equations. But the idea was there, clear and precise, waiting across the centuries for later mathematicians to recognize its profound significance. Euclid's formula can be stated simply. If you take powers of 2 and add them up, starting from 1, and if that sum turns out to be a prime number, then you can create a perfect number. You multiply that sum by the highest power of 2 you used, and the result will be perfect. Let's walk through this slowly, letting each step settle. Start with the number 1. Double it to get 2. Add them. 1 plus 2 equals 3. 3 is prime. Good. Now, take the highest power of 2 you used, which is 2 itself, and multiply it by the sum. 2 times 3 equals 6. And 6, as we know, is perfect. Let's try again. Start with 1. Double it. 2. Double again. 4. Add them all up. 1 plus 2 plus 4 equals 7. 7 is prime. Perfect. Take the highest power of 2, which is 4, and multiply by 7. 4 times 7 equals 28, and 28 is perfect. One more time. Start with 1 and keep doubling. 1, 2, 4, 8, 16. Add them. 1 plus 2 plus 4 plus 8 plus 16 equals 31. 31 is prime. Take the highest power of 2, which is 16, and multiply. 16 times 31 equals 496. Perfect again. Do you see the pattern forming? Every time the sum of powers of 2 is prime, Euclid's formula hands you a perfect number. And all of these perfect numbers are even because you're always multiplying by a power of 2. But here's what Euclid didn't prove, what couldn't be proven for another 2,000 years, that this formula gives you all even perfect numbers, every single one. If an even perfect number exists, it must come from Euclid's formula. There are no other even perfect numbers hiding out there, no exceptions, no alternatives. This stunning fact wasn't proven until the 18th century, when Leonhard Euler, one of history's most prolific mathematicians, finally demonstrated that Euclid's formula was not just sufficient, but necessary. If you want an even perfect number, you must use Euclid's formula. There is no other way. This means that the question of even perfect numbers is intimately connected to a special kind of prime number. Remember that sum we kept checking? 1 plus 2 plus 4 plus 8, and so on? When that sum is prime, it's called a Mersenne prime, named after the French monk Marin Mersenne, who studied them in the 17th century. Mersenne primes are primes of a very specific form. If you take 2 to some power and subtract 1, and the result is prime, you've found a Mersenne prime. 2 to the power of 2 minus 1 is 3, prime. 2 to the power of 3 minus 1 is 7, prime. 2 to the power of 5 minus 1 is 31, prime. Not all powers work. 2 to the power of 4 minus 1 is 15, which isn't prime. But when it does work, you get both a Mersenne prime and, through Euclid's formula, a perfect number. Here's where the story becomes both beautiful and haunting. We found 52 Mersenne primes. We believe there are infinitely many more, though we can't prove it. Each Mersenne prime gives us a perfect number, but all of them, without exception, are even. What about odd perfect numbers? Euclid's formula can't produce them. The formula always multiplies by a power of 2, so the result is always even. If odd perfect numbers exist, they must come from somewhere else, some other pattern, some other formula we haven't discovered. Or perhaps they simply don't exist at all. In our modern age, the search for perfect numbers has become intertwined with the search for Mersenne primes. And that search has become a remarkable story of collaboration, computation, and human curiosity. In 1996, a software engineer named George Waltman founded the great Internet Mersenne prime search, known by its acronym GIMPS. The idea was elegantly simple. Harness the power of thousands of personal computers around the world, each running specialized software in the background, checking candidate numbers to see if they might be Mersenne primes. It worked. It worked spectacularly. Since its founding, GIMPS has discovered 18 of the largest known prime numbers. Each discovery makes headlines. Each new Mersenne prime is larger than the last, pushing into territories of numbers so vast they beggar the imagination. The most recent discovery, as of October 2024, came from Luc Durant, a researcher from San Jose, California. The number he found contains over 41 million digits. If you tried to write it out, filling page after page with digits, it would take more than 20,000 pages. This single number, proved to be prime through a combination of sophisticated algorithms and massive computational power, is now the largest known prime number in existence. But here's what makes this even more remarkable. Durant's discovery was the first to use graphics processing units, or GPUs, rather than traditional computer processors. These are the same chips that power video games and, increasingly, artificial intelligence systems. The future of prime hunting has evolved. Each Mersenne prime discovered by Gibbs comes with a corresponding perfect number. The 52nd perfect number, the one corresponding to Durant's discovery, is a number of staggering size. It's 2 raised to the power of 136,279,840 multiplied by 2 raised to the power of 136,279,841 minus 1. That number is so large that simply storing it in computer memory takes significant space. It's so large that the universe doesn't contain enough atoms to write it out in conventional notation. It's so large that it transcends any practical meaning and exists purely as an abstract mathematical object, a testament to human curiosity and computational power. And it's even. Every perfect number ever found, from ancient 6 to this modern monster, is even. The volunteers who participate in GIMPS come from all walks of life, from all corners of the world. Some are professional mathematicians, most are not. They're teachers, engineers, students, retirees, people who love the thrill of discovery, the possibility of finding something new in the infinite landscape of numbers. They download free software, let it run on their computers during idle time, and wait, sometimes for years, sometimes for decades. When a discovery is made, the finder receives a cash prize, $3,000 for most new Mersenne primes, $50,000 if the discovery is the first to cross certain milestone thresholds. But the real reward, as many participants will tell you, isn't monetary. It's the knowledge that you found something genuinely new, something that didn't exist in human knowledge until the moment your computer finished its calculations. This distributed computing project represents something profound about modern mathematics. It's collaborative, democratic, open to anyone with a computer and curiosity. It's patient, willing to search for years without guarantee of success. And it's beautiful. A collective human effort to push back the boundaries of the known. Yet for all this computational power, for all these discoveries of ever larger Mersenne primes and perfect numbers, the odd perfect number question remains untouched. GIMS cannot help us there. The search for odd perfect numbers requires different tools, different approaches, and despite 20 centuries of effort, that search has turned up nothing. Not a single example, not even a tantalizing near miss. If Euclid opened the door to understanding perfect numbers, it was Leonhard Euler who walked through it and explored the landscape beyond. Euler, the 18th century Swiss mathematician, whose name appears in almost every corner of mathematics, brought his extraordinary analytical powers to bear on the perfect number problem. Euler proved what Euclid could not, that every even perfect number must follow Euclid's formula. There are no exceptions, no alternatives, no other patterns that produce even perfect numbers. If you find an even perfect number, it came from a Mersenne prime. That's the only source. The well is singular. But Euler did something else, something perhaps even more significant for our story. He turned his attention to odd perfect numbers and asked, if they exist, what properties must they have? What restrictions, what conditions, what requirements would an odd perfect number need to satisfy? His analysis was brilliant. Euler proved that if an odd perfect number exists, it must be of a very specific form. It must equal the product of a prime number raised to an odd power, multiplied by a square. Not just any prime, and any square, mind you. The prime must be congruent to 1 modulo 4, meaning that when you divide it by 4, the remainder is 1. This might sound technical, but let's unpack it gently. Euler was saying that odd perfect numbers, if they exist, cannot be made from primes assembled in just any way. They have a structure, a shape, a particular architecture. One prime gets special treatment, raised to an odd power. All the other primes must appear in pairs, squared. Think of it like this. Imagine building a structure from blocks. Euler proved that if you're building an odd perfect number, one block gets to stand alone, raised up high. But all the other blocks must come in matching pairs, stacked beside each other. You can't have 3 of one block or 5 of another, unless they can be grouped into pairs with an extra one left over. This was a remarkable restriction. It meant that odd perfect numbers, if they exist, are not like even perfect numbers. Even perfect numbers have a simple, elegant structure given by Euclid's formula. Odd perfect numbers, if they lurk anywhere in the infinite landscape of integers, must satisfy Euler's conditions. And satisfying those conditions turns out to be extraordinarily difficult. Euler went further. He stated, with characteristic honesty, whether there are any odd perfect numbers is a most difficult question. He wasn't claiming to have solved the problem. He was acknowledging its depth, its resistance to the mathematical tools of his era. Since Euler's time, mathematicians have discovered more restrictions, more conditions, more requirements that any odd perfect number must satisfy. Each new restriction narrows the space where an odd perfect number might hide. Each new condition makes it harder and harder to imagine that such a number could exist. Yet no one has proven impossibility. It's like trying to catch a ghost. Every time you think you've cornered it, you find it must also pass through walls, so you adjust your expectations, accounting for the wall passing. Then you learn it must also be invisible to certain kinds of light. Then you learn it must also be undetectable by sound. Then you learn it must also leave no footprints. At some point, you start to wonder, are we hunting something that exists, or are we proving one condition at a time that ghosts cannot be? Let's take a breath and settle into what modern mathematics has learned about odd perfect numbers. These aren't wild speculations or hopeful guesses. These are proven theorems, mathematical certainties about the properties that any odd perfect number must possess, if one exists at all. First, size. We know that an odd perfect number, should it exist, must be absolutely enormous. Computational searches have checked every number up to 10 to the power of 1500. That's 1 followed by 1500 zeros. The mind cannot grasp such a number. If you tried to count that high, one number per second, you would need more time than the universe has existed, many times more. No odd perfect number exists below this threshold. We know this with certainty. The search has been systematic, exhaustive, checking each candidate methodically, and the search continues to push higher. Though the computational resources required grow exponentially with each new order of magnitude. Second, divisibility. We know that an odd perfect number cannot be divisible by 105. Why 105? Because 105 equals 3 times 5 times 7. Mathematicians have proven that no number divisible by all 3 of these primes can be perfect if it's odd. This doesn't seem like much of a restriction, but it's one more condition, one more hurdle any odd perfect number must clear. Third, modular arithmetic. An odd perfect number must leave a remainder of 1 when divided by 12, or it must leave a remainder of 117 when divided by 468, or it must leave a remainder of 81 when divided by 324. These aren't random conditions. They emerge from deep analysis of how divisors interact, how sums must balance, how the equation of perfection constrains possibility. Fourth, prime factors. This is where things get truly restrictive. An odd perfect number must have at least 9 distinct prime factors, not counting multiplicity, not counting how many times each prime appears, but at least 9 different primes must divide an odd perfect number. Think about that. 6, the first perfect number, has only 2 prime factors, 2 and 3. 28 has 2, 2 and 7. But an odd perfect number? It would need at least 9. And if the number is not divisible by 3, which we've already established is possible, then it needs at least 12 distinct prime factors. Moreover, we know that the total number of prime factors, counting multiplicity, must be at least 101. If a prime appears squared, that counts as 2 factors. If it appears cubed, 3 factors. An odd perfect number must have a staggering number of these, all balanced in precisely the right way to achieve perfection. Fifth, the size of prime factors. The 3 largest prime factors of an odd perfect number must be huge. The largest must exceed 100 million. The second largest must exceed 10,000. The third largest must exceed 100. These aren't the kinds of restrictions you can easily satisfy by accident. And finally, one of the most frustrating restrictions of all. If you write an odd perfect number in the form that Euler described, with 1 prime to an odd power times a square, that square part must be incredibly large. It must exceed 10 to the power of 1,000. That's a 1 followed by 1,000 zeros. Just the square root of an odd perfect number, if 1 exists, would dwarf most numbers humans ever encounter in practical life. All of these restrictions, all of these conditions, are proven theorems. They're not conjectures or beliefs. They're mathematical facts. Any odd perfect number that exists must satisfy all of them simultaneously. It must be larger than 10 to the 1500. It must have at least 9 distinct prime factors, totaling at least 101 factors with multiplicity. Its largest primes must be enormous. It cannot be divisible by 105. It must satisfy particular modular conditions. The web of restrictions is so tight, so constraining, that many mathematicians believe we're watching a proof unfold in slow motion. Each new restriction is another piece of evidence that odd perfect numbers simply don't exist. We're proving impossibility one theorem at a time, narrowing the space where such a number could hide until, perhaps, we finally prove the space is empty. And yet, impossibility has not been proven. The ghost has not been exorcised. The question remains open, tantalizing, frustrating, beautiful in its resistance. Let's drift deeper now into something that lies at the very heart of the odd perfect number mystery, the intricate dance of prime factorization. This is where numbers reveal their innermost structure, where the building blocks of arithmetic come into focus, where we can begin to understand why odd perfection seems so impossibly elusive. Every whole number greater than 1 has a unique prime factorization. This is not a casual observation. It's one of the fundamental theorems of arithmetic proved by Euclid over 2,000 years ago, standing as a cornerstone of all number theory. Every number can be broken down into prime factors in exactly one way. 12 is 2 times 2 times 3, and no other combination of primes multiplies to give 12. 18 is 2 times 3 times 3. 42 is 2 times 3 times 7. The factorization is unique, singular, like a fingerprint identifying each number. This uniqueness is remarkable when you pause to consider it. Imagine if it weren't true. Imagine if some numbers could be factored in multiple different ways, assembled from different sets of primes. Mathematics, as we know it, would collapse. Proof would become impossible. The logical structure we've built over millennia would crumble, but it doesn't. Every number has one and only one prime factorization, and this fact undergirds everything else we know about numbers. Now, when we think about perfect numbers, we're really thinking about how prime factorizations relate to divisor sums. The divisors of a number are determined entirely by its prime factorization. If you know how a number breaks down into primes, you can calculate all its divisors, and from those divisors, you can calculate their sum. The question of perfection becomes a question about prime factorizations that have a very special property. The divisors they generate sum to exactly twice the original number. For even perfect numbers, we know exactly what the prime factorization looks like. It's always a power of 2 multiplied by a Mersenne prime. Always. 6 is 2 times 3, where 3 is a Mersenne prime. 28 is 4 times 7, where 7 is a Mersenne prime. 496 is 16 times 31, where 31 is a Mersenne prime. The pattern is absolute, unbreakable, proven by Euler to be the only way even numbers can achieve perfection. But odd numbers cannot follow this pattern. They cannot be divisible by 2, which means their prime factorization contains no factors of 2 at all. They're built entirely from odd primes: 3, 5, 7, 11, 13, and onward through the infinite sequence of odd primes. And somehow, these odd primes must be combined in such a precise way, raised to such exact powers, that the resulting divisor sum achieves the delicate balance of perfection. Euler showed that if an odd, perfect number exists, one of its prime factors must appear to an odd power, while all the others must appear to even powers. This is a strange asymmetry, a broken symmetry in the factorization. One prime gets special treatment, standing alone with an odd exponent, while all the others come in paired powers, squared or raised to higher even exponents. Why should this be? What forces this particular structure? The proof is technical, involving the properties of multiplicative functions and divisor sums. But the intuition is this: achieving perfection requires a very specific balance between the number and its parts. For odd numbers, lacking the symmetry that powers of 2 provide to even numbers, the balance can only potentially be achieved if the prime factorization has this peculiar, lopsided structure. Let's think about what this means in practice. Imagine you're trying to construct an odd, perfect number. You start with a prime, let's say 3. You raise it to some odd power, let's say to the first power, just 3 itself. Now you need to multiply by squares of other primes to complete your number. You try 3 times 5 squared, which gives 75. Is 75 perfect? Its divisors are 1, 3, 5, 15, and 25. Sum them. 1 plus 3 is 4, Plus 5 is 9. Plus 15 is 24. Plus 25 is 49. But 75 times 2 is 150. 49 is not 150. Not perfect. You try again. Maybe 3 times. 5 squared times 7 squared. That's 3 times 25 times 49, which equals 3,675. Now you'd need to calculate all the divisors, a more tedious task, and check if their sum equals 7,350. The calculations grow quickly unwieldy, but computers can check these things rapidly. And they've checked millions, billions, trillions of such combinations. None work. The challenge is that as you add more prime factors, as you raise primes to higher powers, the relationships between the number and its divisor sum become increasingly complex. You're trying to hit a moving target, trying to balance an equation that has many variables, many degrees of freedom. Each choice of prime, each choice of exponent, changes the divisor sum in ways that interact with all your other choices. Finding a combination that achieves exact balance, that hits perfection precisely, is like trying to solve a multi-dimensional puzzle where every piece you place shifts the positions of all the other pieces. And remember the restrictions we've discussed. The number must be huge, larger than 10 to the 1500. It must have at least 9 distinct prime factors, at least 101 total prime factors, counting multiplicity. The largest prime factor must exceed 100 million. These aren't arbitrary limitations. They're proven requirements, mathematical theorems restricting where an odd, perfect number could possibly hide. Think about the magnitude of these restrictions. 9 distinct odd primes, the smallest being 3, 5, 7, 11, 13, 17, 19, 23, 29. If we multiply just these 9 primes together once each, we get 3,111,696. But that's nowhere near large enough. And besides, we need many more factors, many higher powers, to even approach the complexity required for potential perfection. The more you think about these requirements, the more impossible the task seems. You need a number assembled from many primes in very specific ways, satisfying numerous restrictions, balanced so precisely that its divisor sum equals exactly twice itself. The target is infinitesimally small in the vast space of all possible odd numbers. It's like trying to hit a particular atom in the observable universe by throwing a dart blindfolded from another galaxy. And yet, we cannot prove it's impossible. We cannot demonstrate that the target doesn't exist. All our evidence suggests non-existence. All our intuition points that way, but proof eludes us. Perhaps there's a combination of primes, some extraordinarily large number, with the right structure, the right balance, hiding somewhere beyond our computational reach. Or perhaps, and this seems more likely to most mathematicians, the restrictions are simply too tight, the requirements too demanding, and no such number exists. The prime factorization perspective makes the problem concrete. It transforms the abstract question, do odd perfect numbers exist, into a specific challenge. Can you find a collection of odd primes, raised to appropriate powers, satisfying all the known restrictions, such that the divisor sum equals twice the product? Stated this way, the problem becomes almost tangible, something you could imagine approaching algorithmically, systematically checking possibilities. And that's exactly what computational searches do. They systematically explore the space of possible prime factorizations, eliminating combinations that can't work, testing combinations that might. The process is vast, complex, computationally intensive, but it's concrete, grounded in the reality of prime numbers and their properties. There's something almost mystical about working with infinite sets. Mathematics deals routinely with infinity, treats it as a normal, manageable concept. We speak casually of infinitely many primes, infinitely many perfect numbers potentially, infinitely many integers stretching in both directions from zero. But infinity is not normal. It's not ordinary. It represents something beyond human experience, beyond physical reality, something that exists purely in the realm of abstract thought. When we ask whether odd perfect numbers exist, we're asking a question about an infinite set. There are infinitely many odd numbers. Among that infinite collection, is there even one that's perfect? Or is perfection a property exclusively of even numbers, with odd numbers forever excluded from that exclusive club? The question touches on something profound about infinity. In an infinite set, you'd think anything that's not explicitly impossible must occur somewhere. There are infinitely many odd numbers. Surely somewhere in that infinity, there's one whose devisers sum correctly. Why should perfection be reserved exclusively for even numbers? But infinity doesn't work that way. Infinite sets can have surprising gaps, missing elements that you'd expect to find. Consider the perfect squares: 1, 4, 9, 16, 25, and so on. There are infinitely many of them, and yet most numbers are not perfect squares. In fact, the vast majority of numbers are not perfect squares. Between any two consecutive perfect squares, there are increasingly many non-squares. The squares get rarer and rarer as numbers grow larger, even though there are infinitely many of both squares and non-squares. Or consider primes. There are infinitely many prime numbers, proved by Euclid in one of the most elegant arguments in all of mathematics. And yet, as you count higher, primes become increasingly sparse. The gaps between consecutive primes grow larger on average. The density of primes decreases. Infinity doesn't mean uniform distribution. It doesn't mean everything that could happen does happen. So perhaps odd perfect numbers are like that. Perhaps they're possible in principle, but absent in practice. Perhaps the conditions required for odd perfection are so stringent, so demanding, that even in an infinite set of odd numbers, not one satisfies them all. Perhaps perfection for odd numbers is like finding a needle in an infinite haystack where the needle doesn't exist. This raises deep questions about mathematical existence. What does it mean for a number to exist? In one sense, all numbers exist. They're abstract objects, concepts, ideas with properties and relationships. 3 exists. 7 exists. The square root of 2 exists, even though it's irrational. In this abstract sense, if odd perfect numbers satisfy a coherent definition, don't they exist as a concept? But existence in mathematics often means something more specific. It means you can prove there's at least one example satisfying the definition. Mersenne primes exist because we found 52 of them. Even perfect numbers exist for the same reason. But odd perfect numbers? We have a definition. We know what we're looking for. We just can't find one, and we can't prove none exist. This is the strange territory of mathematical limbo, of questions hanging unresolved between existence and non-existence. The definition makes sense. The concept is coherent. But we cannot produce an example, cannot construct a proof of existence, and we cannot produce a proof of impossibility either. We're suspended in uncertainty, waiting for evidence to tip decisively one way or the other. Some mathematicians find this deeply uncomfortable. Mathematics is supposed to be certain, definitive, clear. Every well-formed question should have a definite answer, but the odd perfect number problem shows that certainty takes time, sometimes lots of time. We've been waiting 2,000 years. How much longer will we wait? Another 1,000 years? 10,000? Forever? There's something humbling about this suspension. It reminds us that human knowledge is not infinite, that our understanding has limits, that some questions are genuinely hard. We've mapped the human genome, split the atom, sent probes to the edge of the solar system, and yet a simple question about odd numbers remains unanswered. The frontier of knowledge is not uniform. Some areas advance rapidly while others lag behind, not for lack of trying, but because the territory is genuinely difficult to explore. The silence of the infinite is the silence of unanswered questions, of possibilities that might exist but remain undiscovered, of territories we cannot yet reach with our mathematical tools. It's the silence of a problem that won't speak, won't reveal its secrets, won't tell us whether the numbers we seek are hiding in infinity's vast expanse or absent entirely. And in that silence, we wait. We continue searching, proving new restrictions, checking higher thresholds, hoping that eventually the silence breaks, the question answers itself, the mystery resolves. But until then, we sit with uncertainty, with not knowing, with the profound humility of confronting a question that remains, after millennia, genuinely open. Even if the odd perfect number problem is never solved, even if it remains forever open, the journey of investigation has taught us enormous amounts about mathematics. This is one of the beautiful paradoxes of mathematical research. Sometimes the questions we don't answer are as valuable as the ones we do, because the attempt to answer them forces us to develop new tools, new techniques, new ways of thinking. Consider all the mathematics that has emerged from studying perfect numbers, the theory of multiplicative functions, the understanding of divisor sums, the connections between primes and perfection, the computational techniques for checking large numbers efficiently. None of this existed in isolation. All of it was developed, at least partly, in service of understanding perfect numbers. The study of Mersenne primes, intimately connected to even perfect numbers, has driven advances in primality testing, in computer algorithms, in distributed computing. The Lucas-Lehmer test, the most efficient known method for checking whether Mersenne numbers are prime, is a beautiful piece of mathematics that wouldn't exist without the motivation of finding large primes. And finding large primes has applications far beyond perfect numbers, in cryptography, in random number generation, in various areas of computer science. The restrictions on odd perfect numbers, all those conditions we've discussed, required proving sophisticated theorems about prime factorizations, about modular arithmetic, about the behavior of multiplicative functions. Each theorem is a contribution to number theory, a piece of knowledge that stands on its own, independent of whether odd perfect numbers exist. We've learned about the structure of integers, about how primes interact, about the subtle relationships between numbers and their divisors. The computational searches have driven innovation in algorithm design, in optimization, in parallel processing. How do you efficiently search vast ranges of numbers? How do you eliminate impossible cases quickly? How do you coordinate searches across multiple computers? These are not trivial questions, and solving them requires creativity and technical skill. The techniques developed transfer to other computational problems, benefiting areas of science and technology far removed from pure mathematics. There's also a pedagogical value. Perfect numbers are an excellent way to teach number theory. They're easy to define, interesting to explore, rich in mathematical content. Students can understand the basic question immediately, then gradually learn the more sophisticated mathematics required to study it seriously. It's a gateway into deeper mathematical thinking, a problem that grows with you as your understanding develops. And there's inspiration, the persistence of the odd, perfect number problem, its resistance to solution, serves as a reminder that mathematics still has frontiers, still has mysteries, still has questions that challenge the brightest minds. In an age where students sometimes feel that everything worth discovering has already been discovered, problems like this offer hope, possibility, the promise that there's still work to be done, still territories to explore. The problem also teaches patience and humility. Not every question yields quickly to attack. Not every problem has an obvious solution path. Sometimes you work for years without making meaningful progress. Sometimes the mountain is too high to climb in one generation. But that doesn't make the work meaningless or the question unworthy. It just means mathematics is hard, genuinely hard, and some problems demand persistent effort across time. There's a kind of mathematical wisdom that emerges from working on unsolved problems. You learn to value small advances, to appreciate incremental progress, to find satisfaction in ruling out impossibilities even when you can't prove your conjecture. You learn to work collaboratively, building on others' work and leaving foundations for those who come after. You learn to take the long view, understanding that your contribution might be just one small step in a journey that spans centuries. And perhaps most importantly, you learn to be comfortable with uncertainty. Mathematics is often taught as a subject of certainty, of definitive answers, of clear right and wrong. But at the research frontier, uncertainty is the norm. You don't know if your approach will work. You don't know if the problem is solvable. You don't know if your efforts will bear fruit. You proceed anyway, guided by curiosity and hope, making progress where you can, accepting failure when it comes. These are lessons that transcend mathematics. They're lessons about how to approach any difficult problem, how to persist in the face of uncertainty, how to value the journey even when the destination remains unclear. They're lessons about patience, humility, collaboration, and the quiet satisfaction of doing good work even when success is not guaranteed. The odd, perfect number problem has been teaching these lessons for 2,000 years. It has trained generation after generation of mathematicians in the virtues required for deep investigation. And regardless of whether it's ever solved, it will continue teaching these lessons to future generations, serving as a test, a challenge, a reminder that some questions resist easy answers and demand our very best thinking. Mathematics, at its heart, is about stories. Not stories in the traditional narrative sense, but stories about patterns, about relationships, about structures underlying reality. When we prove a theorem, we're telling a story about why something must be true. When we discover a formula, we're revealing a story about how quantities relate to each other. And when we encounter an unsolved problem, we're in the middle of a story whose ending we don't yet know. The odd perfect number problem is one of mathematics' longest-running stories. It begins in ancient Greece with Euclid's discovery of how to generate perfect numbers. The story continues through medieval times when Islamic mathematicians preserved and extended Greek knowledge, calculating larger perfect numbers, wondering about the possibility of odd ones. It flows through the Renaissance and Enlightenment as European mathematicians like Mersenne and Euler made their contributions, adding chapters to the narrative. The story accelerates in modern times, with computational searches and new theoretical results arriving regularly. Each paper proving a new restriction, each computational threshold surpassed. Each theorem about necessary conditions adds a paragraph to the ongoing story. We're living in the middle of this narrative, watching it unfold in real time, unable to see the ending, but privileged to witness the journey. But here's what's interesting. We don't know what kind of story this is. Is it a mystery story, where the detective slowly accumulates clues until finally identifying the culprit? In this case, either finding an odd, perfect number or proving none exist. Is it a tragedy, where despite our best efforts, we never reach resolution, never answer the question? Is it a comedy, where the answer turns out to be obvious in hindsight once someone has the key insight? Is it an epic, a grand adventure spanning millennia and involving thousands of characters all pursuing a common goal? We can't know until the story ends, if it ever does. And that uncertainty is part of what makes the problem fascinating. We're participants in a narrative whose genre and outcome remain unknown. We're writing the story as we live it, each contribution adding to a collective work whose final chapter might not be written for centuries or millennia. This narrative dimension of mathematics is often overlooked. We focus on the technical content, the theorems and proofs, the calculations and algorithms. But behind all that technical apparatus is a human story, a story of curiosity and persistence, of collaboration across time and space, of individuals and communities working together to push back the boundaries of knowledge. The odd perfect number problem connects us to everyone who has thought about it before. When you contemplate this question, you're joining a conversation that includes Euclid, Mersenne, Euler, and thousands of others across centuries. Your thoughts become part of the ongoing narrative. Your contributions add to the collective understanding. You're a character in a story much larger than yourself, a story that began before you were born and will continue after you're gone. And perhaps that's enough. Perhaps being part of the story, contributing even a small amount to the collective knowledge, is reward sufficient. Perhaps we don't need to see the ending to find meaning in the journey. Perhaps the story itself, the shared human project of understanding, is what matters most. In 1638, the French philosopher and mathematician René Descartes was corresponding with the monk Marin Mersenne about perfect numbers. In one of his letters, Descartes presented an intriguing discovery. He had found a number that was almost perfect, almost but not quite. The number Descartes found was 19,858,557,618 and 9. It's the product of 3 squared times 7 squared times 11 squared times 13 squared times 22,021. Descartes calculated the sum of this number's divisors and found something remarkable. If only 22,021 were prime, this number would be perfect. Its divisors would sum to exactly twice the number itself. It would satisfy the definition. It would be an odd perfect number. But 22,021 is not prime. It equals 100. 79 times 123. It's composite, made from smaller primes, and that ruins everything. The calculation doesn't quite work. The divisors sum to slightly more than twice the number. Descartes had found what we now call a spoof number, or sometimes a Descartes number. It's a number that would be perfect if only one of its composite factors were prime instead. Is tantalizingly close, a near miss, a number that whispers the possibility of odd perfection while ultimately falling short. For 361 years, Descartes' spoof stood alone. It was the only known example of a number with this property. Then, in 1999, mathematician Jon Voight discovered a second one. His number was negative, involving a negative prime factor, which makes it even stranger. But it had the same fundamental property: change one composite factor to prime, and you'd have a perfect number. Since then, more spoof numbers have been found. Each one tantalizes. Each one suggests that odd perfect numbers might be possible, that we're just one lucky arrangement of primes away from finding one. And yet, each one ultimately disappoints, failing the test by a small but decisive margin. Some mathematicians have suggested that studying spoof numbers might be the key to proving that odd perfect numbers don't exist. If we can understand exactly what makes spoof numbers fail, if we can catalogue all the ways a number can come close to perfection without achieving it, perhaps we can prove that actual perfection is impossible for odd numbers. Pace Nielsen, a mathematician who has contributed significantly to our understanding of odd perfect numbers, has argued that spoof numbers deserve more attention than they've received. They're not just curiosities or near misses. They're data points, examples of how the equation of perfection almost works for odd numbers. They show us the boundary between possible and impossible, even if we can't yet prove which side of that boundary odd perfect numbers fall on. The existence of spoof numbers raises a philosophical question that echoes through all of mathematics. Is close enough ever close enough? In the realm of perfect numbers, the answer is a definitive no. A number is either perfect or it isn't. There's no partial credit, no almost perfect that counts. The divisors either sum to exactly twice the number or they don't. There's no room for approximation, no tolerance for error. And yet, the spoof numbers persist in our catalogues, reminding us that odd perfection is at least conceivable, at least mathematically close to possible. They're like footprints leading to a door that might not exist, evidence of something that might be just beyond our reach, or might be nowhere at all. In the age of computers, the hunt for odd perfect numbers has become a matter of raw computational power combined with mathematical cleverness. It's not enough to simply check every odd number one by one. That approach would take far longer than the universe has existed. Instead, mathematicians have developed sophisticated algorithms that can eliminate vast swaths of possibilities at once. The current record, maintained by researchers Pascal Ockham and Michael Rao, stands at 10 to the power of 1500. Their computational search has verified that no odd perfect number exists below this threshold. To put this in perspective, 10 to the 1500 is incomprehensibly large. The observable universe contains approximately 10 to the 80 atoms. The number of seconds since the Big Bang is around 10 to the 18. 10 to the 1500 dwarfs these numbers by so many orders of magnitude that comparison becomes meaningless. How do they do it? How can a computer search space this vast? The key lies in the restrictions we discussed earlier. You don't check every number. You use mathematical theorems to eliminate billions or trillions of possibilities at once. For instance, if you know an odd perfect number must have at least 9 distinct prime factors, you don't bother checking numbers with fewer factors. If you know it must be congruent to 1 modulo 12, you skip all the numbers that aren't. If you know certain primes cannot divide an odd perfect number, you eliminate all multiples of those primes. Layer these restrictions, combine them cleverly, and you can narrow the search space dramatically. Not enough to make it trivial, mind you. The computational work is still staggering, requiring specialized algorithms running on powerful computers for extended periods, but it becomes feasible, possible, achievable within human lifetimes. The algorithms used in these searches are themselves works of art. They employ number-theoretic sieves, techniques borrowed from the search for prime numbers. They use factor chains, analyzing how prime factors must relate to each other if perfection is to be achieved. They exploit modular arithmetic, checking remainders rather than full numbers when possible. They leverage mathematical structure in every way imaginable to reduce the computational burden. But despite all this cleverness, despite all this computational power, the searchers have found nothing. No odd perfect number, not one. The higher the searchers push, the more the absence becomes conspicuous. It's like searching an ever larger haystack for a needle that might not exist. Each search that finds nothing is evidence, weak evidence, but evidence nonetheless, that the needle isn't there. Some computational searches focus not on finding an odd perfect number, but on proving they can't exist below certain thresholds. Others focus on narrowing the conditions, proving that odd perfect numbers, if they exist, must satisfy even more restrictive requirements. Both approaches contribute to the slowly tightening net of evidence and restriction. There are also distributed computing efforts, similar to GIMPs, but focused on odd, perfect numbers. Volunteers donate computer time, running specialized software that checks candidate numbers. These efforts move slowly compared to the Mersenne prime search, largely because the algorithms are more complex and the restrictions harder to exploit. But they persist, driven by the same curiosity that motivates all mathematical exploration. The emotional journey of these searches is fascinating. There's excitement at the start, the thrill of entering unexplored territory, of checking numbers no human has ever examined. There's the daily grind of waiting for computations to complete, the slow accumulation of negative results. And there's the philosophical question that becomes harder to ignore with each passing year. Are we searching for something real? Or are we slowly proving a negative? No one knows how high the computational searches will need to go before the mathematical community accepts that odd perfect numbers likely don't exist. 10 to the 1500 is already beyond comprehension. 10 to the 1600 would be even more so. At what point does absence of evidence become evidence of absence? At what point do we stop searching and start believing the ghost isn't there? Step back from the calculations for a moment. Step back from the prime factors and the modular arithmetic and the computational searches. Look at the odd, perfect number problem from a distance, as a whole, as a question that has persisted across millennia. What does it mean for a mathematical problem to remain unsolved for 2,000 years? What does it tell us about the nature of mathematics, the limits of human knowledge, the structure of the universe itself? Some problems remain unsolved because they're obscure, buried in technical details that few people care about. The odd perfect number problem is not one of these. It's simple to state, elegant to understand, accessible to anyone who can add and multiply. And yet it resists solution with a stubbornness that borders on the supernatural. Some problems remain unsolved because we lack the right tools, the right frameworks, the right perspectives to attack them. Perhaps this is true of odd perfect numbers. Perhaps somewhere in the future, a new mathematical framework will emerge that makes the problem suddenly tractable, solvable, obvious in hindsight. Or perhaps the problem is unsolvable, not because we lack tools, but because the answer is no, and proving non-existence is fundamentally harder than proving existence. Think about what existence versus non-existence means in mathematics. If odd perfect numbers exist, we only need to find one example. A single odd number whose divisors sum to twice itself. One example would settle the question forever. Every mathematician would gather around, verify the calculation, and the mystery would be solved. But if they don't exist, we need to prove a universal negative. We need to show that among all the infinitely many odd numbers, not one satisfies the perfection condition. We need to demonstrate impossibility across an infinite domain. That's a much harder task, requiring not just examples, but proof, not just evidence, but logical certainty. This asymmetry shapes how mathematicians think about the problem. Most believe odd perfect numbers don't exist. The evidence points that way. The restrictions are too tight, too constraining. The computational searches go too high without finding anything. The whole structure of requirements seems designed to make existence impossible. And yet, belief is not proof. Intuition is not certainty. Until someone proves that odd perfect numbers cannot exist, the question remains open. The possibility lingers. The ghost might yet materialize. Karl Pomerantz, a number theorist who has thought deeply about this problem, has presented what he calls a heuristic argument for non-existence. It's not a proof, but a probabilistic analysis suggesting that the odds of an odd perfect number existing are essentially zero. His reasoning involves estimating how many numbers satisfy various necessary conditions and showing that the probability approaches zero as you combine more and more restrictions. It's a compelling argument, but it's not a proof. Mathematics demands certainty, and heuristic arguments, no matter how convincing, fall short of that standard. We can believe, we can be almost certain, but almost isn't enough. There's something beautiful about this uncertainty, though. Something valuable about a problem that resists easy solution. The odd perfect number problem has inspired countless papers, countless hours of thought, countless innovations in number theory and computation. It has taught us about divisors, about primes, about the intricate relationships between numbers. It has driven the development of algorithms and computational techniques that have applications far beyond this single question. In a sense, the journey is more valuable than the destination. The search for odd perfect numbers has enriched mathematics, whether or not odd perfect numbers exist. And perhaps that's enough. Perhaps the value lies not in solving the mystery, but in wrestling with it, in pushing against the boundaries of knowledge, in refusing to give up even when the answer seems determined to remain hidden. You might wonder, as you lie there listening, why anyone cares about odd perfect numbers. They have no practical application. They won't cure diseases, won't improve technology, won't solve any real-world problems. If they exist, so what? If they don't, who cares? This is a fair question. It deserves a thoughtful answer. Mathematics is not always about utility. It's not always about application or practical benefit. Sometimes mathematics is about beauty, about pattern, about understanding the abstract structures that underlie reality. And sometimes mathematics is about the simple human drive to know, to understand, to answer questions because they're there. Perfect numbers have fascinated humans since ancient times because they represent a kind of mathematical balance, a harmony between a number and its parts. 6 is perfect because its parts, when combined, recreate the whole. It's self-contained, complete, a little pocket of mathematical elegance. The question of whether odd, perfect numbers exist is a question about how deep this pattern goes, how universal this balance is. If only even numbers can be perfect, that tells us something profound about the structure of arithmetic, about how divisibility works, about the relationship between a number and its factors. If odd perfect numbers do exist, that would be equally profound. It would show that mathematical harmony can arise in unexpected ways, that the patterns we think we understand can surprise us. It would open new avenues of investigation, new questions to ask. But beyond the specific facts about perfect numbers, this problem represents something larger. It represents the frontier of human knowledge, the boundary between what we know and what we don't. For 2,000 years, the greatest mathematical minds have grappled with this question. For 2,000 years, it has resisted solution. That persistence, that resistance, tells us something about the limits of knowledge, about how hard some truths are to reach. There's also a historical dimension worth considering. This problem connects us to the ancients, to Euclid in Alexandria, to medieval monks copying manuscripts, to Renaissance scholars rediscovering classical knowledge, to Enlightenment mathematicians developing new tools, to modern researchers wielding computational power unimaginable to earlier generations. It's a continuous thread of human curiosity spanning millennia. When you think about odd perfect numbers, you're thinking thoughts that Euclid thought. You're asking questions that puzzled Euler. You're engaging with a mystery that has captivated genius after genius, generation after generation. There's something humbling and connecting about that. We're part of a long conversation, a dialogue across time about the nature of numbers and the limits of understanding. And finally, there's the simple beauty of the question itself. Not all valuable things are useful. Not all meaningful pursuits have practical outcomes. Sometimes beauty is enough. Sometimes wonder is enough. Sometimes the simple fact that a question can be asked cleanly and clearly is reason enough to seek an answer. The odd perfect number problem is a pure expression of mathematical curiosity. It's a question stripped of context, of application, of utility. It exists in the realm of pure abstraction, pure thought. And in that purity, it has a kind of crystalline elegance that makes it worth pursuing for its own sake. Whether or not odd perfect numbers exist, the search for them has value. The restrictions we've discovered, the computational techniques we've developed, the theorems we've proved along the way, all contribute to our understanding of numbers and their properties. The journey enriches mathematics, even if the destination remains unknown. So where does the problem stand today? What are mathematicians doing now to try to crack this ancient puzzle? One active area of research involves tightening the known restrictions even further. Every few years, someone manages to prove that odd perfect numbers, if they exist, must satisfy yet another condition, must exceed yet another threshold, must have yet another property. These incremental advances may not sound exciting, but each one narrows the space where an odd perfect number could hide. Pace-Nielsen, whose work we mentioned earlier, has been particularly active in this area. His papers use sophisticated factor chain arguments combined with computational verification to prove results like odd perfect numbers must have at least 9 distinct prime factors. Each such result is a small victory, another piece of the puzzle. Another approach involves studying related problems. What about almost perfect numbers? Numbers whose divisors sum to almost twice themselves. What about multiply perfect numbers? Numbers whose divisors sum to 3 times themselves or 4 times, or any multiple. By understanding the broader landscape of these related concepts, mathematicians hope to gain insight into the specific case of odd perfection. There's also increasing interest in using modern computational tools, not just to search for odd perfect numbers, but to search for patterns in the restrictions themselves. Perhaps there's a meta pattern, a deeper structure to all these conditions that would make a proof suddenly possible. Machine learning algorithms are being applied to mathematical problems with increasing success. Could artificial intelligence spot a pattern that human mathematicians have missed? Some researchers are exploring connections between perfect numbers and other areas of mathematics. Algebraic number theory, modular forms, analytic techniques, all might shed light on the problem from unexpected angles. Sometimes, the key to solving an old problem is not to attack it directly, but to approach it from a completely different field, using tools that weren't available when the problem was first posed. There's also philosophical work being done on what it would mean to solve the problem. If computational searches eventually reach 10 to the 2000 or 10 to the 10,000 without finding an odd perfect number, at what point do we accept non-existence? Mathematics traditionally requires proof, not just overwhelming evidence. But perhaps for some problems, the standards need to evolve. Karl Pomerantz's heuristic argument for non-existence represents a different kind of approach. Instead of trying to prove impossibility directly, it uses probabilistic reasoning to argue that existence is overwhelmingly unlikely. This doesn't satisfy the strict requirements of mathematical proof, but it does provide a framework for thinking about the problem in new ways. The development of quantum computers might eventually affect the search. Quantum algorithms can solve certain types of problems much faster than classical computers. Whether they could accelerate the search for odd perfect numbers depends on whether the problem can be reformulated in ways that quantum computers excel at. This remains an open question, but it's one that researchers are exploring. There's also ongoing work on related number-theoretic problems that might provide insights. The distribution of prime numbers, the behavior of divisor functions, the properties of multiplicative functions, all connect in various ways to the question of odd perfect numbers. Breakthroughs in these related areas could potentially illuminate the main question. One particularly intriguing line of research involves trying to prove that odd perfect numbers would have to be so large, satisfy so many conditions, have so many prime factors, that their existence becomes mathematically incoherent. It's like proving that a shape would need to have both 3 sides and 4 sides simultaneously, an obvious contradiction. We're not there yet, but some mathematicians believe we're moving in that direction. The use of computer-assisted proofs has become increasingly common in mathematics. Some major theorems have been proved with essential help from computers, checking millions of cases that would be impossible to verify by hand. Perhaps the odd perfect number problem will eventually yield to a similar approach, with computers not just searching for examples, but helping to construct proofs of impossibility. Whatever approaches ultimately prove successful, if any do, the path forward involves a combination of human creativity and computational power, theoretical insight and practical verification, old techniques and new technologies. It's a collaboration across time and tools, bringing together all the resources that mathematics has developed over its long history. As we drift toward the end of our exploration, let's pause to appreciate something that might seem paradoxical: the beauty of not knowing. Mathematics is often presented as a subject of certainty, of definitive answers, of problems solved and theorems proved, and much of it is. But mathematics also has its frontiers, its edges, its places where knowledge gives way to mystery. And these places have their own kind of beauty. The odd perfect number problem has remained unsolved for 2,000 years, not because mathematicians are incompetent or lazy. It has remained unsolved because it is genuinely, profoundly difficult. It touches on deep aspects of how numbers work, aspects that we still don't fully understand despite millennia of study. There's something humbling about this. We've sent humans to the moon. We've split the atom. We've decoded the human genome. We've built computers that can simulate entire universes. And yet, a question that a child could understand about whether odd numbers can be perfect remains beyond our grasp. This should not discourage us. It should inspire us. It should remind us that there are always deeper questions, always more to learn, always mysteries waiting to be explored. The frontiers of knowledge are not fixed. They're constantly expanding, but they're also constantly revealing new unknowns beyond themselves. The odd perfect number problem connects us to something larger than ourselves, larger than our time, larger than our individual understanding. It's a problem that Euclid contemplated, that Euler worked on, that thousands of mathematicians across centuries have thought about. When we think about it, we join that long chain of curiosity, that human tradition of wondering and questioning and seeking. And perhaps the problem will never be solved. Perhaps it's one of those questions that will remain forever on the frontier, forever tantalizing, forever just out of reach. If so, that's okay too. Not every question needs an answer. Not every mystery needs to be solved. Sometimes the value lies in the asking, in the wondering, in the exploration itself. The poet Rainer Maria Rilke wrote, "Be patient toward all that is unsolved in your heart, and try to love the questions themselves." This could be a motto for mathematics, or for any deep human endeavor. Love the questions, embrace the mystery. Find beauty not just in answers, but in the spaces where answers haven't yet arrived. The odd perfect number problem is one of those beautiful unsolved questions. It's a space in mathematics where we don't yet know, where we might never know, where the journey of exploration is ongoing and open-ended. And in that openness, in that uncertainty, there's a kind of freedom and possibility that solved problems don't offer. So as you lie there, drifting towards sleep, or drifting in that pleasant space between waking and dreaming, let the odd perfect number problem sit gently in your mind. Don't try to solve it. Don't try to force an answer. Just let it be there, a small, elegant question, a thread connecting you to millennia of human curiosity, a reminder that the universe still holds mysteries, that knowledge still has frontiers, that some questions remain beautifully, frustratingly, wonderfully open. We've traveled a long way tonight, from ancient Alexandria to modern supercomputers, from Euclid's elegant formula to the endless restrictions that any odd perfect number must satisfy. We've seen how a simple question about whether odd numbers can be perfect has resisted solution for over 2,000 years. We've learned that perfect numbers are rare, precious things, numbers whose divisors sum to exactly themselves. We've learned that all known perfect numbers are even, arising from Mersenne primes through Euclid's formula. We've learned that odd perfect numbers, if they exist, must be enormous, must have many prime factors, must satisfy countless restrictive conditions. We've seen how computational searches have pushed into unimaginable territories, checking numbers so large they dwarf the universe itself, finding nothing. We've explored the restrictions, the conditions, the requirements that narrow the space where an odd perfect number could hide. We've met the mathematicians who've devoted their careers to this problem, from ancient scholars to modern researchers. We've seen the clever techniques they've developed, the algorithms they've created, the theorems they've proved in pursuit of an answer. And we've found that after all this work, after all this thought, after all these centuries, the question remains open. We don't know if odd, perfect numbers exist. We don't know if they don't exist. We're balanced on a knife's edge of uncertainty, with strong evidence suggesting non-existence, but no definitive proof either way. This is the nature of deep mathematical problems. They resist easy solution. They require patience, persistence, creativity, and sometimes more than a little luck. They remind us that knowledge is not a destination, but a journey, that understanding is not a state, but a process, that some questions take generations to answer, or longer. The odd perfect number problem may be solved tomorrow. Some graduate student might wake up with a brilliant insight. Some computer might stumble on an example during its nightly calculations, or the problem might remain unsolved for another 2,000 years, or forever. The search for odd, perfect numbers provides a fascinating window into how technology has transformed mathematical research. A problem that ancient Greeks could formulate and ponder, but barely begin to investigate practically, is now being attacked with computational tools that would seem like magic to mathematicians from even a century ago. Consider what's involved in checking whether a large number is perfect. You need to find all its divisors, add them up, and compare the sum to twice the number. For a small number, this is trivial. For 6, you check 1, 2, and 3. Add them, get 6. Done. For 28, a bit more work but still manageable by hand. For 496, you'd want paper and patience, but it's doable. But for truly large numbers, the kind that might be odd perfect numbers if they exist at all, hand calculation becomes absurd. Numbers larger than 10 to the 1500 have more digits than there are particles in the observable universe. You cannot write them down completely, let alone manually calculate their divisors. You need computers, powerful ones, and clever algorithms to make the computation feasible. The development of these algorithms is itself mathematically interesting. You can't just try dividing by every number smaller than your candidate. That would take far too long, longer than the age of the universe, even for computers billions of times faster than what we have. You need to be smart. You need to use the restrictions we've discovered to eliminate vast ranges of candidates without checking them individually. You need to exploit number-theoretic properties to speed up divisor calculations. This interplay between theory and computation, between pure mathematics and practical algorithm design, characterizes modern number theory. The two feed each other. Theoretical results enable more efficient computation. Computational results suggest new theoretical investigations. It's a productive symbiosis, each side strengthening the other. The GIMPS project exemplifies this relationship perfectly. Finding Mersenne primes requires both theoretical understanding, knowing which numbers to check and which to skip, and computational power, actually performing the Lucas-Lima test on enormous candidates. The project has discovered the largest known prime numbers by combining these elements effectively. Distributed computing provides the raw power. Number theory provides the strategic direction. Could a similar distributed effort accelerate the search for odd, perfect numbers? In principle, yes. In practice, it's more difficult. The space to search is less structured than the space of potential Mersenne primes. The tests are more complex. The restrictions are harder to exploit computationally, but efforts are being made. Volunteers are contributing computer time. Slowly, patiently, the lower bound increases. There's also the question of what counts as proof in the age of computers. Traditionally, mathematical proof meant logical deduction from axioms, checked and verified by human mathematicians. A proof was a sequence of reasoning steps, each followable by a trained human mind. Computers played no essential role, but modern mathematics increasingly involves computer-assisted proofs. The four-color theorem was first proved using extensive computer checking of thousands of cases. And the Kepler conjecture about sphere packing was proved using computers to verify complex calculations. These proofs are controversial, not because anyone seriously doubts their correctness, but because they represent a shift in what mathematical proof means, a proof that no human could verify completely by hand, that relies essentially on computational verification, challenges traditional notions of mathematical rigor. The odd perfect number problem hasn't yet reached this stage. We haven't found a proof, computer-assisted or otherwise, that odd perfect numbers don't exist. But if such a proof is found, it might well involve computational elements. It might require checking a finite but enormous number of cases, too many for human verification. Would that count as a proof? Most mathematicians would say yes. If the computation is verifiable and the theoretical framework sound, but it would still mark a shift in how we think about mathematical knowledge. There's something both exciting and unsettling about this. Exciting because it expands what we can prove, what questions we can answer. Unsettling because it removes proof from the realm of pure human reason into something requiring machine assistance. The democratization of verification becomes harder when proofs require significant computational resources to check. But this is the direction mathematics is moving. Computers are tools, like pencil and paper, like symbolic notation, like any of the technological aids that have enabled mathematical progress. They extend our capabilities, allow us to explore territories previously inaccessible. The odd perfect number problem. Whether it's ultimately solved by pure reasoning or computational assistance, will likely involve computers in some essential way. The age of purely human mathematical investigation may be drawing to a close, replaced by human-machine collaboration. This shift raises interesting philosophical questions. If a proof requires a computer to verify, is it truly understood by humans? If understanding means being able to follow every step of reasoning, and the reasoning includes billions of computational steps, can anyone claim to understand the proof? Or does understanding mean something different in this new era? Perhaps grasping the overall strategy and trusting computational verification for the details. These questions don't have easy answers. They're being debated by philosophers of mathematics, by working mathematicians, by anyone who cares about the nature of mathematical knowledge. The odd perfect number problem, sitting at the intersection of pure theory and computational practice, embodies these tensions perfectly. Mathematics is not a collection of isolated problems. It's a web of interconnected ideas, each thread touching many others, each question connecting to a dozen more. The odd perfect number problem, while distinctive in its longevity and simplicity, is no exception. It connects to numerous other areas of mathematics, sometimes in surprising ways. The most obvious connection is to prime number theory. Perfect numbers are intimately related to primes. Even perfect numbers come from Mersenne primes. Odd perfect numbers, if they exist, must have specific prime factorizations. Understanding primes helps us understand perfect numbers, and vice versa. Results about prime distribution, prime gaps, prime factorization, all potentially bear on the perfect number question. There's also a deep connection to the theory of multiplicative functions. The sum of divisors function, usually denoted sigma, is a multiplicative function, meaning that if two numbers are coprime, the sigma of their product equals the product of their sigmas. This property is fundamental to much of the analysis of perfect numbers. Understanding multiplicative functions more broadly could shed light on when and why divisor sums equal specific multiples of their arguments. Perfect numbers also connect to abundant and deficient numbers, and to the broader classification of numbers by their abundancy index, the ratio of divisor sum to the number itself. Perfect numbers have abundancy index exactly 2. Abundant numbers have index greater than 2, deficient numbers less than 2. There's an entire theory of numbers classified by this index, with perfect numbers sitting at a special critical value. Some researchers have investigated whether the abundancy index can take on all rational values greater than 1. If it can, then finding odd numbers with abundancy indices very close to 2 might help us understand why hitting exactly 2 seems impossible for odd numbers. This is the territory of near-perfect numbers, of almost perfect numbers, of the spoof numbers we discussed earlier. There are also connections to amicable numbers and sociable numbers. Amicable numbers come in pairs where each number's proper divisors sum to the other number. 220 and 284 are the smallest amicable pair. Sociable numbers extend this to longer cycles. These are all variations on the theme of divisor sums equaling or relating to the original numbers in special ways. Understanding one type might illuminate the others. Perfect numbers also appear in recreational mathematics, in number puzzles and curiosities. Martin Gardner, the famous mathematical recreationalist, wrote extensively about perfect numbers. They have a charm, an elegance that appeals to puzzle enthusiasts and amateur mathematicians. This broader interest has kept the problem alive in popular culture, ensuring it doesn't get forgotten in the specialized literature of professional number theory. There are even connections to computer science, algorithms for factoring large numbers, for computing divisors efficiently, for checking primality. All relevant to the perfect number search, have applications in cryptography and other areas. The RSA encryption system, which secures much of modern internet commerce, relies on the difficulty of factoring large numbers. While perfect numbers aren't directly used in cryptography, the mathematical techniques overlap significantly. Some mathematicians have even speculated about connections to more abstract areas like algebraic number theory or algebraic geometry. Could perfect numbers have interpretations or generalizations in these broader frameworks? Could techniques from these areas shed new light on the classical problem? These are speculative questions, explorations at the frontier of mathematical research, but they illustrate how even an ancient, elementary problem can connect to the most modern and abstract mathematics. The web of connections means that progress on odd, perfect numbers might come from unexpected directions. A breakthrough in prime distribution theory might suddenly make certain approaches viable. An advance in computational number theory might enable new search strategies. A new theoretical framework from a completely different area of mathematics might provide the key insight that finally cracks the problem. You never know where the solution will come from, which is part of what makes mathematical research exciting and unpredictable. Let's talk about something rarely discussed in mathematics: the virtue of patience. Mathematics is often presented as a subject of sudden insights, of brilliant flashes of understanding, of eureka moments, and those do happen, but far more common is slow, patient, methodical work, grinding away at a problem day after day, month after month, sometimes year after year, with no guarantee of success. The odd perfect number problem exemplifies this aspect of mathematical research. No one will solve this problem in a flash of inspiration. It's too hard, too deep, too resistant to easy approaches. If it's solved at all, it will be through patient accumulation of results, through systematic exploration of the mathematical landscape, through careful checking of possibilities and elimination of impossibilities. Think about the computational searches. Someone sets up a program to check numbers up to some threshold. The program runs for hours, for days, for weeks, checking candidate after candidate, finding nothing. Eventually, it finishes. The result: no odd perfect number exists below this threshold. A negative result, but a result. The threshold gets recorded. The search parameters are adjusted. A new, higher threshold is set. The program starts again. The process repeats. This is not glamorous work. It's not the stuff of mathematical legend, but it's essential. Every threshold that's checked and cleared is progress. Every restriction that's proved tightens the net. Every theorem about necessary conditions narrows the space of possibility. Slowly, incrementally, patiently, our understanding grows. Or consider the theoretical work. A mathematician starts exploring whether odd perfect numbers must satisfy some new condition. They try various approaches. Most lead nowhere. Dead ends, false starts, calculations that don't work out. But occasionally, rarely, one approach shows promise. They pursue it, work through the details. Check and double-check their reasoning. Write it up carefully. Submit it for publication. Wait months for referee reports. Revise based on feedback. Eventually, maybe, the result gets published. One more small piece of the puzzle falls into place. This process can take years. A single theorem might represent thousands of hours of work, and that theorem might be just one small step toward the ultimate goal of understanding odd, perfect numbers. The destination remains distant. The work continues. There's something almost meditative about this kind of patient investigation. You're not trying to force an answer. You're not rushing toward a conclusion. You're sitting with the problem, examining it from different angles, letting your understanding deepen gradually. It's mathematics as contemplation, as sustained attention, as disciplined inquiry over time. This patience is partly why the problem has remained unsolved for so long. It's genuinely difficult, yes, but it's also the kind of problem that doesn't yield to impatience, to hurried thinking, to shortcuts. It demands care, thoroughness, systematic exploration. It rewards patience, punishes haste. It's a teacher of virtue, training mathematicians in the qualities required for deep investigation. And there's a kind of faith required too. Faith that the work matters, even if you don't solve the problem yourself. Faith that your small contribution adds to the collective understanding. Faith that eventually, perhaps generations from now, someone will put all the pieces together and find the answer. You're working on a project bigger than yourself, bigger than any individual. You're part of a tradition, a lineage of seekers, a chain of investigators stretching back to antiquity and forward to unknown futures. This is very different from the image of mathematics often presented in popular culture. The lone genius, the brilliant insight, the sudden solution. Those moments happen, but they're not the whole story, maybe not even the main story. More often, mathematics is patient collaboration across time, is accumulated small insights is systematic exploration guided by careful reasoning. It's a marathon, not a sprint. And the odd, perfect number problem is one of the longest marathons in all of mathematics. We've spent our time tonight wandering through one of mathematics' most enduring mysteries. From ancient Alexandria to modern supercomputers, from Euclid's elegant formula to the seemingly impossible restrictions on odd perfect numbers, from the thrill of Mersenne prime discoveries to the patient, grinding work of computational searches, we've met mathematicians across millennia, united by curiosity about a simple question: can odd numbers be perfect? And after all this exploration, after all this history, after all this investigation, the answer remains: we don't know. We suspect they don't exist. The evidence points that way. The restrictions are so tight, the conditions so demanding, the computational search is so thorough. But suspicion is not proof. Evidence is not certainty. Until someone proves impossibility or finds an example, the question remains genuinely open. There's something beautiful about this uncertainty. Something humbling about confronting a question we cannot yet answer. In our age of instant information, of searchable knowledge bases, of AI systems that can answer questions about almost anything, here's a question that resists all our tools, all our cleverness, all our computational power. A simple question that a child could understand. Can an odd number's proper divisors sum to the number itself? And we don't know. After 2,000 years, we still don't know. This is not a failure of mathematics or mathematicians. It's a testament to the depth of mathematical reality, to the genuine difficulty of some questions, to the fact that knowledge has limits and frontiers. We've pushed those frontiers remarkably far. We've discovered restrictions, proved theorems, developed algorithms, checked vast ranges of numbers. But the ultimate question remains unanswered. And perhaps that's okay. Perhaps some questions are meant to remain open, to challenge generation after generation, to serve as reminders of what we don't yet know. Perhaps the journey of investigation is itself the reward, the growth in understanding more valuable than any final answer. Perhaps wrestling with unsolved problems is what keeps mathematics alive, dynamic, vital. The odd perfect number problem will continue. New mathematicians will encounter it, become fascinated by it, contribute their insights to the collective understanding. New computational techniques will push the search boundaries higher. New theoretical frameworks might provide the key to finally solving it. Or it might remain unsolved for another 1,000 years, or 2,000, or forever. Whatever happens, the problem itself, in its simplicity and difficulty, its accessibility and profundity, remains a jewel of mathematics, a question worth asking, worth pondering, worth wrestling with, whether or not we ever find the answer. And sometimes, on quiet nights like this one, simply thinking about such questions, simply sitting with the mystery, is enough. The numbers continue their infinite march. Perfect numbers appear at rare intervals, like stars in the vast night of arithmetic. Odd numbers, our familiar companions from childhood counting, keep their secrets, perhaps hiding perfection among their ranks, perhaps not. And we, curious humans that we are, continue to ask, to search, to wonder, to dream of the day when this ancient mystery finally yields its truth. Thank you for this journey through mathematical time, through the landscape of perfect numbers, through one of humanity's longest-running investigations. May it bring you not anxiety, but peace, not confusion, but a pleasant kind of mental drift, the satisfaction of having brushed against deep mystery and come away enriched rather than frustrated. May the numbers guide you gently into dreams where perhaps odd, perfect numbers wait to be discovered, if only in the realm of imagination. Sweet dreams and good night.